The situation involves an electrical service upgrade for a school, specifically a 120/208 volt, three-phase system initially utilizing a single set of 500 kc mil cables. The proposed additional load is significant at 228 kilowatts or 750 amps. The local utility Con Edison has ruled that a service reinforcement is needed. The plan involves installing two 4-inch conduits and one additional set of 500 kc mil service cables. The key question revolves around the customer's ability to tap into this new service. The correct interpretation is that Con Edison will provide the additional conduits and one set of 500 kc mil cables, and the customer will then be permitted to tap into these cables with a maximum of 3 sets of 500 kc mil cables total, including the existing set. Therefore, the initial set and then 2 additional sets would reach this maximum amount. This interpretation hinges on the understanding that Con Edison is augmenting the existing service infrastructure to accommodate the increased load demand. The implications are as follows. Con Edison is responsible for installing 2 new 4-inch conduits in addition to the pre-existing conduit. Con Edison will provide and install 1 additional set of 500 kc mil service cables. Following Con Edison's installation, the customer is permitted to tap into the expanded service with a maximum of 3 sets of 500 kc mil cables. To ensure accuracy, verifying with a Con Edison representative assigned to the project is essential, as interpretations can vary and official documentation takes precedence. When dealing with electrical service upgrades and utility rulings, several factors must be considered. Firstly, the National Electrical Code, or NEC, plays a crucial role in dictating safe and compliant electrical installations. Secondly, local amendments and utility-specific requirements often supplement the NEC, adding another layer of complexity. Thirdly, understanding the specific terminology and drawings provided by the utility is paramount for proper implementation. The NEC provides guidelines for conductor ampacity based on size, insulation type, and installation method. For instance, Table 310.15b16 in the NEC outlines the allowable ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air and various raceway configurations. A 500 kc mil copper conductor with a 75 degrees Celsius insulation rating, commonly THHN or XHHW, typically has an ampacity of around 380 amps in a raceway. However, ampacity derating factors must be applied when multiple conductors are bundled together in a conduit or when the ambient temperature exceeds specified limits. NEC Section 310.15c addresses ampacity adjustment factors for more than 3 current carrying conductors in a raceway or cable. The adjustment factors decrease the allowable ampacity to prevent overheating. For example, if there are 4 to 6 current carrying conductors in a raceway, the ampacity must be reduced to 80% of its original value. For 7 to 9 conductors, the reduction is to 70%. In this particular scenario, the existing and new conductors will likely be installed in separate conduits, mitigating the need for significant derating due to conductor bundling. However, ambient temperature considerations still apply. If the service entrance is located in a hot environment, such as near a boiler room or in direct sunlight, the conductor ampacity must be further derated. The NEC provides tables for temperature correction factors based on the conductor's insulation rating and the ambient temperature. In addition to conductor ampacity, the overcurrent protection for the service must be carefully selected. The overcurrent protection device, typically a circuit breaker or fuses, must be sized to protect the conductors from overload and short circuit conditions. NEC Section 240.4 outlines the requirements for overcurrent protection of conductors. The overcurrent protection device should not exceed the conductor's ampacity after derating factors have been applied. For example, if a 500 kc mil conductor has a derated ampacity of 304 amps, the overcurrent protection device should not exceed 300 amps, using the next lower standard size. Furthermore, the service equipment must have an adequate short circuit current rating, or SCCR. The SCCR is the maximum fault current that the equipment can safely withstand without causing catastrophic failure. The available fault current at the service entrance is determined by the utility's transformer capacity and impedance. The service equipment's SECR must be greater than or equal to the available fault current. Coordination studies are often performed to determine the available fault current and to ensure that the overcurrent protection devices are properly coordinated. Coordination ensures that the overcurrent device closest to the fault will trip first, minimizing the extent of the outage. In this scenario, Con Edison's requirement for service reinforcement indicates that the existing service was inadequate to handle the additional load. The addition of two 4-inch conduits and one set of 500 kc mil cables is intended to increase the service capacity and reliability. The customer's ability to tap into these cables with a maximum of 3 sets of 500 kc mil cables provides flexibility for future load growth. However, it is crucial to ensure that all conductors, overcurrent protection devices, and service equipment are properly sized and installed in accordance with the NEC and local regulations. The two 4-inch conduits provide ample space for the conductors and allow for future expansion. The NEC specifies the maximum allowable conduit fill, which is the percentage of the conduit's cross-sectional area that can be occupied by conductors. Chapter 9, Table 1 of the NEC provides the conduit fill requirements. For 3 or more conductors, the maximum allowable fill is 40%. Using a larger conduit size allows for easier conductor pulling and reduces the risk of conductor damage during installation. When installing the conductors, it is important to follow proper cable pulling techniques. Lubrication should be used to reduce friction and prevent insulation damage. The pulling tension should be monitored to ensure that it does not exceed the conductor's maximum allowable pulling tension. The NEC provides guidelines for conductor pulling tension in section 300.18. After the conductors are installed, they should be properly terminated at the service equipment. The termination should be clean and tight to ensure a good electrical connection. Torque specifications should be followed when tightening the terminations to prevent overheating and premature failure. The service equipment should be properly grounded and bonded in accordance with the NEC. Grounding provides a path for fault current to return to the source, tripping the overcurrent protection device and preventing electrical shock. Bonding ensures that all metal parts of the electrical system are at the same potential, reducing the risk of electrical shock. NEC Article 250 provides the requirements for grounding and bonding. Before energizing the new service, it is important to perform a thorough inspection to ensure that all work has been completed correctly and that all safety requirements have been met. The inspection should include verifying conductor ampacity, overcurrent protection sizing, grounding and bonding, and proper terminations. Once the inspection is complete and all deficiencies have been corrected, the new service can be energized. It is also advisable to perform infrared scanning to check for hotspots after energization. The NEC provides extensive guidance on electrical installations, covering various aspects such as wiring methods, overcurrent protection, grounding, and equipment installation. Adhering to the NEC and local regulations is essential for ensuring a safe and reliable electrical system. Therefore, to reiterate, the customer is allowed to tap into these cables with a maximum of 3 sets of 500 kc mil cables. This is the most accurate interpretation of the scenario. Always confirm with the utility representative.